Welcome to part 2 of this lecture on inferences for proportions. We're now going to look at the one-sample z-test for a proportion. Often, researchers, they're interested in using a proportion from a random sample to generalize to a population. So examples include, is the proportion of people voting for a politician greater than 0.5? Is the proportion of people who support marijuana legalization less than 0.6? Is the proportion of people who are Catholic greater than 0.20? Each of these examples, there's some claim made about a proportion in the population. We're interested in using a random sample of data and a sample proportion from that random sample to test these claims about proportions in the population. We conduct the one-sample z-test for a sample proportion to test these kinds of claims. And there are several steps. First of all, the preliminaries include you want to state the target population. What population are you testing? Is it all people living in the United States? Is it all people living in Germany? Or is it some subset? Maybe it's only employed people. Maybe it's all women. So the first step is to state your population. Then you want to state the parameters of interest. So in this case, we're interested in the population proportion. But it's always good to double check, because maybe you're actually interested in some other quantity about a population. Maybe it's a sample, the mean of that population that you're interested in. And then, of course, when we deal with a proportion, we want to check the success-failure condition. Again, this is an assumption about the population, but we can use our sample proportion to assess how confident we are in terms of violating or meeting that success-failure condition. Then we have, once these preliminaries are out of the way, we have several steps. We have 5 steps. The first step is to state the null and alternative hypotheses in terms of H subscript 0 and H subscript A. Then we select the significance level alpha. That's our probability of a type 1 error. Then for step 3, we compute the test statistic for this one-sample proportion. For a one-sample z-test for a sample proportion, it is a test statistic that is a z-test statistic, just like before. Then for step 4, we have sort of 2 options. You assume the null is true. So what this really is saying, we're assuming that, hey, I think that that sampling distribution, it's centered on whatever the null value is, right? Whatever the null is, that's where the sampling distribution we think is centered. And then what we do is we make a decision based on comparing the test statistic z with some critical value or values, and then we compare the p-value with the significance level alpha. You can do A or B or both. Typically, we will do both. Then you state your conclusion. Make sure to state it in substantive terms. Try to interpret your findings. And then, of course, I always highly recommend that you calculate a confidence interval. Okay? This is very useful because a traditional confidence interval is equivalent to a two-sided test. So you can compare the null value with the range of plausible values from a 1 minus alpha times 100% confidence interval. So let's go through these steps. Step 1, you state the hypotheses. The null hypothesis is almost always an equality, and we use p subscript 0 to refer to that claimed value for the population proportion. So the null is that p equals p subscript 0. Then the alternative hypothesis is almost always one of these options. For a two-sided z-test, the alternative is simply that that population proportion does not equal that claimed value of that proportion. A right-sided z-test is that the population proportion is in fact greater than the claimed value of the null hypothesis, and the left-sided test is that population proportion is less than the claimed value of the null hypothesis. For step 2, we choose our significance level alpha. Now, this is the criterion that we use for statistical significance. Typically, in the social sciences, we use an alpha of 0.05. The selection of alpha is important because it affects how we make a decision based on the p-values. So it's the benchmark by which we compare whether p-value is low. Selecting alpha also affects our critical values by which we can compare the test statistic. And then alpha also affects our confidence intervals, because a confidence interval is 1 minus alpha times 100 for a particular percent for a confidence interval. So selecting alpha affects the width of our confidence interval, it affects our critical values, and it affects our p-values, all the benchmarks by which we use to compare our test statistic. And of course, remember that alpha is simply the probability of a type 1 error or false alarm. So in some fields, they're more comfortable with a higher probability of a false alarm, whereas other fields, they're less comfortable with that. So they might select an alpha of 0.01 rather than 0.05. For step 3, we compute the test statistic. So for a one-sample z-test for sample proportion, the z-test statistic is simply p hat, right, that sample proportion minus p subscript 0, that claimed value of the population proportion divided by the standard error. And the standard error is calculated by p subscript 0 times 1 minus p subscript 0 divided by n, and then you take the square root of that quantity. So for a hypothesis test, we typically calculate that standard error using that claimed value of that population proportion. Right? Again, this is just called a z-test statistic for a proportion. Just like with the mean, this test statistic tells us how far a sample proportion p hat is from the claimed proportion p subscript 0 of the null hypothesis. To put another way, the one way to think about a hypothesis test is that p subscript 0, that claimed value of the population proportion, right, we assume that's true. So we assume that the sampling distribution is centered around that claimed value of the population proportion. Then we calculate our point estimate, we calculate p hat, and then we compare how far off, how different is p hat from p subscript 0, assuming p subscript 0 is really where that sampling distribution is located. Right? Just because from sampling variability, we know that most of the values for these sample proportions should be pretty close to that middle part of that sampling distribution. Right? Again, the more extreme that test statistic, the more inconsistent the data is with our null hypothesis. And the more inconsistent the data is with our null hypothesis, we're going to reject that null. For step 4a, we can compare the test statistic with some critical value or values. So this is one way of really formally making a decision based on a sort of extreme test statistic. So the critical value, recall it's based on that significance level of alpha. So for a two-sided test, right, where the population proportion does not equal the claimed value of the population proportion, if the absolute value of that z-test statistic is greater than z alpha divided by 2, then we're going to reject that null. For a right-sided test, where the alternative is that the population proportion is greater than the claimed value of the null hypothesis, then if our test statistic is greater than or equal to z alpha, we reject the null. For a left-sided test where the alternative is the population proportion is less than the claimed value, if our test statistic is less than or equal to negative z alpha, then we reject the null. For each of these instances, we compare our z-test statistic to some critical value, right, based on alpha. And the basic idea is that if our test statistic lies in a rejection region, if it is more extreme than the critical value, then we can reject the null hypothesis. Another way to really make a decision is to compare our probability or p-value to some significance level alpha, or an alpha criterion level, it's sometimes called. So the p-value is the probability value. Now be careful here because the p-value is often called p, so make sure to read the context. Is p referring to the population proportion, or is it referring to the p-value? Well, the p-value is simply the probability of obtaining a test statistic as or more extreme than the one we actually obtained. So for a two-sided test, where the alternative is the population proportion does not equal the claimed value under the null, the p-value is simply the probability of obtaining a z-test statistic greater than or equal to the one we obtained in absolute value times 2. We multiply by 2 because we want to take into account the fact that we might have really extreme positive or really extreme negative test statistics. For a right-sided test, where the alternative is that the population proportion is greater than some claimed value of the null, then the p-value is simply the probability of obtaining a test statistic greater than or equal to the one we obtained. And then for a left-sided test, where the alternative is that the population proportion is less than the claimed value of the null, a p-value is simply the probability of a test statistic less than or equal to the one we obtained. For each of these three kinds of alternatives, right, we reject the null if the p-value is less than or equal to alpha, where alpha is set beforehand. Typically, we set alpha to 0.05, but again, in different fields, in different contexts, you might use a different level of alpha. Once you've made a decision, you make a conclusion. Right? And we make a decision to reject or fail to reject the null based on the previous step, 4A or 4B. Of course, it is important never to stop here. Interpret your conclusion substantively. The important point here is that statistical significance may not equal substantive significance. Ask yourself, Does the null make sense? Maybe you're rejecting a null hypothesis that is not really that interesting. So make sure to really consider what your findings are telling you. And then finally, of course, I recommend always to calculate a confidence interval. So for a sample proportion, the confidence interval is p hat plus or minus z alpha divided by 2 times the standard error, where the standard error is calculated using p times 1 minus p divided by n, and you take the square root of that quantity. Now, of course, we typically use, when we calculate a confidence interval, in this case, we'll want to use their value of p hat, or point estimate, as an estimate for p when we calculate a confidence interval. And you can, intuitively, you can kind of view this as a two-sided z interval test. So with that, we've gone through the major steps for hypothesis testing when you have a sample proportion. Now we're going to go through a few instances, a few examples of going through these particular steps for a sample proportion.